All right, let's talk about radicals. When we're talking about a radical, there are several components to it. We use a radical for something like a square root or a cube root, but you'll notice you've got your radical sign right here. The number that is here is called your index, and the value that is underneath the radical sign is called your radicand. Now, if there is no number where the index is, then we assume that that number is going to be a 2, and we call that a square root. So that square root symbol represents the principal square root, which is just a non-negative number, a positive number. What we mean by that is even though 5 squared is 25 and negative 5 squared is 25, when you see the square root of 25, we are going to assume that that is the non-negative or the positive value. Now, if you're thinking, wait, I thought I was supposed to insert a plus or minus when I put in a square root. You're exactly right, but you didn't put in this square root. This one was already here. So when the radical is already there, we assume that it is the positive one. If you insert the square root, then yes, you insert a plus or minus with it. Now, a couple of rules of radicals. If you have the square root of two values, you can break that into two separate square roots. And the reverse of that is also true. If you have the square root of a times the square root of b, you can combine that into a single square root ab. And that would also be true if you had a cube root or something else. But the key is that the index has to be the same to be able to combine these. I couldn't do like the square root of a and the cube root of b. Same idea with the quotient. You can go either way with if you have a fraction, you can break it into two separate pieces, or if you have two separate pieces, you can combine them under one single fraction, again, as long as the index is the same. So let's look at a couple of examples, all right? For the first one, we've got the square root of 144. So here's the idea behind a radical. What I'm looking for is I want to try and rewrite 144 as some value squared. The reason for that is that a square root and a square are going to undo each other. They're going to cancel each other out. So that square root and square cancel each other out and just leave me with 12. Same idea with a cube root. If I have a cube root, I want to try and rewrite 8 as some value cubed. So, of course, the 8 can be written as 2 cubed. And again, the cube root and the cube will drop each other out. They're inverses. They cancel each other out, and that would leave me with just 2. All right, let's think about negative 8. If you take a number and cube it and get negative 8, what would that be? Well, negative 2 cubed is negative 8. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. And so again, your cube root and your cube can cancel each other out and just give you negative 2. All right, look at the next one. So for the next one, we've got the cube root of 16. I'm going to rewrite 16 as 8 times 2. Why would I do that? Well, because over here, we've already seen that we can simplify the cube root of 8 down to 2. So if I have the cube root of 16 and I rewrite it as the cube root of 8 times 2, I'm going to use our product rule right up here. That enables me to write this as two separate radicals. So I can write that as the cube root of 8 times the cube root of 2. So as we saw, the cube root of 8 was 2. I can go ahead and simplify that one. So if the cube root of 8 is 2, I don't have any way to simplify this cube root of 2. So I just bring it straight down, and that is actually my final answer, is 2 cube roots of 2. All right, so this is about as complicated as we're going to get here. So let's look at this next one. For this next one, I have several things that are being multiplied. So let's use our product rule again, and let's break this up into separate pieces so it's a little bit easier to work with. So I'm going to take each one of these and write them as a separate radical. All right, so let's start with the square root of 8. All right, so the square root of 8, now of course the cube root of 8 is 2. But 8 is not a perfect square. Like 2 squared is 4, 3 squared is 9. 8's somewhere in between there. So I'm going to rewrite it. 8 is 2 cubed, as we've already seen. 2 cubed would be the same thing as 2 squared times 2, right? 2 squared times 2 to the first is 2 cubed. All right, so then I can break that into two separate pieces, and I can say, okay, that'd be the square root of 2 squared times the square root of 2. Square root of 2 squared times the square root of 2. And of course, as we've already talked about, the square root and the square drop each other out to just leave me with 2. I can't simplify that square root of 2 at all, so I'll just bring it along. All right, then I look at the square root of a. The only way that I can eliminate that square root is if I have a squared. Since I don't have a square, there's really nothing I can do with that. All right, so let's move along to the next one. And let's look at the square root of c cubed. I want to think of this the exact same way I did that 2 cubed. If you'll notice, I broke it up into 2 squared times 2. So I'm going to do the same thing here. I'm going to break this up to c squared times c. And then, just as we did with our product rule, we could break this into two separate radicals. I'm going to do the same thing. I'm going to break this up into two separate radicals. So then I can say the square root of c squared. The square root and the square cancel each other out. Can't do anything with this square root of c, so it's just left over. So the exact same way it worked with a number. When I had the square root of 2 cubed, I got 2 square roots of 2. When I had the square root of c cubed, I got c square roots of c. All right, so constants or variables are going to work the same way. All right, then let's look at d to the fourth. So d to the fourth I could rewrite as d squared times d squared. And then using my product rule again, I could say that that's two separate pieces. And so then the square root of d squared, the square root and the square would drop each other out and leave me d. Here, the square root of d squared, the square root and the square would drop each other out and leave me with d. So d times d is d squared. Another way that you could think about that is, what squared is d to the fourth? Well, yeah, d squared squared is d to the fourth. So that might be another way you could think of that. Okay, so let's see what we've got now. We've got 2 square roots of 2. We've got the square root of a that we couldn't do anything with, so let's just bring it down. C square roots of c and d squared. So when I write this, I want to collect all the pieces that are outside of the radical. So you'll notice I've got the 2, I've got the c, and I've got the d squared that are outside the radical. So I'm going to put all those together. And then I want to collect all the pieces that are under the radical. So I have a 2, I have an a, I have a c. So let's combine all those pieces. And so that would be our final answer, 2cd squared, square roots of 2ac. All right, so remember we talked about combining like terms. And we said that when you were combining like terms, you had to have the same variable to the same exponent. Very similar with radicals. You can combine radicals if they have the same index and the same radicand. When we combine like terms, we just combine the coefficients. So we're going to do the same thing here. We're just going to combine the coefficients, and we're going to leave the radical the same. So look at this first one. So for this first one, I've got 3 square roots of 2, square root of 8, and square root of 2. I cannot combine those as they are because you cannot combine unless your index and your radicand are the same. So yes, my index is the same, square root, square root, square root, but my radicand is not. Here I have a 2, here I have a 2, but here I have an 8. So let's see if we could maybe simplify that square root of 8. You might remember we just worked with that one on the previous example, and we got the square root of 8 was 2 square roots of 2. Now we have like terms because our radicals are the same. Square root of 2, square root of 2, square root of 2. So to combine them, I'm going to combine my coefficients. Now, what's the coefficient of this square root of 2 right here? I have 1 square root of 2, right? So that coefficient is 1. So let's combine our coefficients. 3 plus 2 minus 1 is going to give us 4. And then we keep our radical exactly the same. The index and the radicand do not change. So it would be just as if you had 3x plus 2x minus 1x, you would get 4x. So it's the exact same idea. I have 3 square roots of 2 plus 2 square roots of 2, that's 5 of them, minus 1 square root of 2, so that leaves only 4 of them. All right, this next one's a little more complex, so let's look at that one together. All right, so to begin with, as we've seen with our product rule, we've got several things going on here, so it might be easier to break that into separate pieces. All right, so I'm going to have the square root of 36, the square root of a squared, the square root of b to the 4th, the square root of c, and then over here, square root of 16, square root of a squared, square root of b to the 4th, square root of c. So again, just using that product rule to break all those into separate pieces. All right, so what's the square root of 36, right? Square root of 36 is 6, so we already had our 2. Square root of 36 is 6. What's the square root of a squared? The square root and the square drop each other out and just give me a. What's the square root of b to the 4th? We saw that just a moment ago with d to the 4th, that you could think of that as b squared times b squared. And so the square root of b to the 4th would be b squared. And then I can't do anything with the square root of c, because again, to simplify that, I'd have to have at least 2 of them, and I don't, so I'm going to have to leave that guy exactly as it is. All right, now let's come to the second term down here. So we've already got our 4. What's the square root of 16? Square root of 16 is 4. Square root of a squared is a. Square root of b to the 4th is b squared. And I can't do anything with that square root of c. All right, so if we simplify just a little bit here, 2 times 6, of course, is 12, and 4 times 4 is 16. So I have 12ab squared square roots of c minus 16ab squared square roots of c. And if you'll notice, ab squared square roots of c, ab squared square roots of c. These are like terms. So to combine them, I'm just going to combine the coefficients. So for my coefficients, I have 12 minus 16. So 12 minus 16 is going to give me negative 4. And then I keep my term exactly the same. I keep the variables and the exponents and the radical exactly the same. So ab squared square roots of c. All right, so we've done a lot with our product rule. Now we want to work some more with our quotient rule, all right? So look at this first one. We have 2 square roots of 160 over the square root of 10. In our quotient rule, it said that if you had one radical being divided by another, as long as their index was the same, that you could combine them under one single radical. So I'm going to leave my 2 out here out of the way. And I'm going to combine these into one single radical. Why would I want to do that? Because I don't know how to break down the square root of 160 simply, and the square root of 10 is not going to break down. But if you'll notice, when I combine them, 160 divided by 10, I can simplify. 160 divided by 10 is 16. That's much easier to work with because, of course, the square root of 16 would be 4. And so then I can say 2 times 4 is going to give me 8. All right, look at another one of those. All right, so this time I have my 2 radicals already combined. So I want to see, as we did a second ago, is there any way to maybe simplify what's under the radical? All right, so both of those numbers are even, so they're at least divisible by 2. So that would give me the square root of 5 over 36. And then I'm going to use the quotient rule in the reverse way that we did last time. Last time we had 2 separate pieces we combined into one. This time I have one piece that I want to break apart into 2 separate pieces. So I'll write it as 2 separate radicals. All right, so if I look at my numerator, square root of 5, I can't simplify that. But my denominator, what's the square root of 36? Well, the square root of 36 is 6. And so that would give me square root of 5 over 6. Now, for my radical to be in its most simplified form, I'm not allowed to, if I have a fraction, I'm not allowed to have a radical in the denominator. And so when I get to this next example, I have a problem because I have a radical in the denominator, and that won't be in its most simplified form. So the way that I can get rid of that is I can multiply by its conjugate. Now, a conjugate is the exact same number, so you can see the 1 in the square root of 5, 1 in the square root of 5. It's the exact same numbers, but it's the opposite sign in between them. So because this one was positive, this one's going to be negative. And of course, whatever I multiply the bottom by, I have to multiply the top by so that I don't change anything. All right, so if we go through and multiply, in my numerator, I've got 4 times that quantity, 1 minus the square root of 5. So I'll leave that as it is. In my denominator, I'm going to need to FOIL. So I've got 1 plus the square root of 5 times 1 minus the square root of 5. So if we FOIL, I'm going to have 1 times 1 is 1. 1 times the negative square root of 5 is a negative square root of 5. Positive square root of 5 times 1 is a positive square root of 5. And positive square root of 5 times the negative square root of 5 would be a negative square root of 25 or a negative 5. So one more time, positive square root of 5 times negative square root of 5. Positive times negative is negative. Square root of 5 times square root of 5 is square root of 25 or 5. All right, so if you'll notice, these two guys right here in the middle are opposites of each other, and they'll cancel each other out. And that was my goal. If you'll notice, we just got rid of our radical in the denominator. Perfectly fine to have a radical in the numerator. You just cannot have a radical in the denominator for your answer to be in its lowest terms. Okay, so let's finish simplifying this. I'm going to leave that numerator alone for right now. So in my denominator, I'm going to have 1 minus 5. So 1 minus 5, of course, would be negative 4. All right, then I could cancel this 4 in the numerator with the 4 in the denominator. And if I do, that's just going to leave me a negative 1. So you could think of it as 4 divided by negative 4 is a negative 1 times 1 minus the square root of 5. If you'd rather distribute that negative 1, you could do that as well. And so that'd be negative 1 plus the square root of 5. You could write it either way. All right, let's look at one more. So for this next one, again, when I'm looking at this, I cannot leave a radical in the denominator. So I want to try and simplify this. And again, I'm going to use that quotient rule and the product rule, whatever I have at my disposal. All right, so to begin with, I'm going to use the product rule to break all of this apart. So I've got the square root of 25 times the square root of x to the 11th times the square root of y. And then down here in the bottom, same thing, square root of 49 times square root of x to the 7th times square root of y. And I've just put my numbers together and put my x's together and put my y's together. All right, so looking at this first piece right here, I don't want to combine this under a single radical because I can simplify it as it is. Like, what's the square root of 25? Well, it's 5. What's the square root of 49? It's 7. But for this next piece, I don't know what the square root of x to the 11th is. I don't know what the square root of x to the 7th is. Those aren't perfect squares. And so in this case, I am going to use my quotient rule, and I'm going to combine those under a single radical. Because if I put x to the 11th over x to the 7th in a single radical, what do you do when your bases are the same and you're dividing? Well, you can combine them then by saying x to the 11th minus 7, right? So when your bases are the same and you're dividing, you subtract your exponents. So that would give us 11 minus 7, or 4. Similarly, over here, if I combine the square root of y over the square root of y and do one radical, y over y would just be 1. They would drop each other out, and so I would just have the square root of 1. All right, so we're going to keep our 5/7 as it is. The square root of x to the 4th would be x squared, and the square root of 1 would just be 1. So in my numerator, I'm going to have 5x squared, and in my denominator, I'm going to have 7. All right, next thing we want to talk about are rational exponents. All right, all that means is that our exponents are fractions. So if you'll notice here, we've got a to the m over n. That's the same thing as a to the m, and then the nth root of that. So you'll notice your numerator remains your exponent, your denominator becomes your index. So one more time, if you have something raised to a fraction, the numerator will be your exponent, the denominator will be your index. Now, there is not an order of operations here that says that you have to do this exponent first before you do this radical. You can do the radical first and then do the exponent. And we'll see in just a second that that will make it a whole lot easier for us a lot of times. All right. So an example of that, if you have 4 to the 1/2, that numerator is going to be your exponent. So that'd be 4 to the 1. And that denominator is going to be your index. So that would be a square root right there. And remember, when it's a 2, we don't have to write it. So square root of 4 would just be 2. So 4 to the 1/2 would just be 2. All right, so look at the next one. We've got 8 to the 4/3. Okay, so we know we're going to have the square root of 8. So what number is going to be my exponent? Well, the numerator, 4, is going to be my exponent. And then the denominator, 3, is going to go right here and be my index. So that would be the cube root of 8 to the 4th. Now, if I had to find 8 to the 4th first, that would not be a lot of fun. 8 times 8 times 8 times 8, and I'd get a humongous number. And then I got to try and take the cube root of that humongous number. So remember we said up here that there's not an order of operations. You do not have to do the exponent first. You can do the radical first and then raise it to the exponent. So look how much simpler this is. If I do the cube root of 8 first, we've already done that earlier today. The cube root of 8 is 2. So then I just have 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. I can do that in my head and not have to do crazy 8 to the 4th and get some humongous number. Now, if you want to do that on your calculator to check it, notice that if you just type it straight into your calculator, 8 to the 4/3, sure enough, your calculator will verify that answer for you as well. Okay, so not only can we take the rational exponent and write it as a radical, we can go the opposite way. We can take the radical and write it as a rational exponent. All right, so for this example, we're going to leave the 4 alone, but let's come down here and look at the denominator. So for our denominator, we're going to have a to the something, all right? So what's our numerator going to be? Well, remember that the exponent is your numerator and the index is your denominator. So for us, our exponent, 2, is going to be our numerator, and our index, 7, is going to be our denominator. So that would be a to the 2/7. If we didn't want to have that a to the 2/7 in the denominator, we can move it up to the top using a negative exponent. So remember that if you have a negative exponent, that just causes it to move across the division bar. So to move this a to the 2/7 up to the top, I would just make it a negative exponent. Either one of these would be identical. They would be the same answer. All right, look at the next one. So for the next one, I'm going to start off by getting my constants, 5 times 2 times 3. Now, remember, you can multiply in any order. 2 times 3 times 4 is the same thing as 2 times 4 times 3 is the same thing as 3 times 4 times 2. So there's nothing that says that I have to do 5 times 2 times x to the 3/5. I can do 5 times 2 times 3, then times x to the 3/5 and x to the 1/5. So I'm going to do that. I'm going to put my constants together and I'm going to put my variables together. All right. So over here, 5 times 2 is 10 times 3 is 30. And then when your bases are the same and you're multiplying, what do you do to your exponents? Well, you add them. So 3/5 plus 1/5 is going to give us 4/5. So we'll have 30x to the 4/5. Or if they told us that they wanted to write that, they wanted us to write that with a radical, then again, your numerator is your exponent, your denominator is your index. So we could write that as the 5th root of x to the 4th. Either one of those would be the same. All right, look at one more. So for this one, we start off with 16/9 to the negative 1/2. All right, how do we get rid of that negative? We said that to get rid of a negative exponent, you move across the division bar, or you flip it. So this 16 is being raised to a negative 1/2, and this 9 is being raised to a negative 1/2. So to get rid of the negative, I'm going to move the 16 across the division bar, it goes to the bottom, and I'm going to move the 9 across the division bar, it goes to the top. So in essence, that fraction just flips. So I would end up with 9/16 to the positive 1/2. All right, so then what does 1/2 mean? Well, the numerator is my exponent, the denominator is my index, so I could rewrite that as the numerator is my exponent of 1, the denominator is my index of 2 for a square root. So that would just be the square root of 9/16. So square root of 9 is 3, square root of 16 is 4, and so 3/4 would be our final answer.